So meanwhile, you are joining in, guys. Can you just tell us from which place are you in? Maybe which city, which country you are in? So I'm based on Bangalore, and Nikhil, we have from New York. So yeah,
Hey,
all
yo.
good. Anyone from Bangalore? Good. So we have Kerala, Toronto, Pune. Nobody from Bangalore, I believe.
Oh, wow. It's very diversified places.
So Chennai, Mumbai, nice. This seems to be really online only, right?
Yeah, I know. This is awesome. Usually in the meetups, like I kind of, if you are regular in a meetup group, you kind of know everyone. Now, since it's becoming online, it's kind of nice to see people from all over different places joining the meetups. And this is
Right.
gonna have a wider reach, I guess. This is awesome.
And I think people also watch these videos post the session
Y-
also. So people do
Correct.
kind of sign up for the RSVP there so that they can get the links there. So we're already live on YouTube. So people already just click on the YouTube link and join in there as well. So
Nice.
Thomas from Seattle, nice. Okay, so I think it's the time. We should get going. So let me just go over. So good evening, everyone, and good morning, wherever you are. So thanks for joining in this online Kubernetes and Cloud Native meetup. This is the sixth meetup what we are doing. We started in somewhere around March, and then within this whatever the lockdown period we have, right, we could finish six, and then I think all of them has been different topics. So yeah, so let me just get going. So in the today's session, we are going to cover two things. One is Kubernetes as storage orchestrator. That would be done by me, and then we'll have Nikhil, who is going to kind of talk about distributed SQL with YugaByteDB. So these are two topics we're going to cover. So I'm going to kind of take around in half an hour, and then we'll have Nikhil to kind of finish for the remaining 1 hour, and he can kind of go further as well if needed, if you have more questions. So all that is fine.
Yep.
Uh, so yeah, let's get going, guys. My name is Nipendra Khare, and I'm founder of CloudYuga. And with CloudYuga, we provide consulting and training in the area of Kubernetes, cloud native technologies stuff. I also authored the official CNCF Kubernetes course on which is on edX. It has been taken by more than 100K participants around the world. I'm also CNCF ambassador and certified administrator as well for Kubernetes, and done a book on Docker 2015 long back. Yeah. Yeah, so in the today's first half of the session, we are going to cover the topics listed here. Primarily, going to see what are traditional and software-defined storage are available. I mean, they're there, and then we have been using them for some time. And then what happens with the containers? How we can attach the containers and the storage. Then we look at some quick overview of how does Kubernetes manage volumes. Then we'll see static and dynamic volume provisioning. And then effectively we'll kind of jump into that the orchestration of storage via Kubernetes. There we'll cover container attached storage or CAS, and we'll see the benefits and the example of CAS. And then if time permits, I'll have a quick demo of Rook there. Traditionally, if you look at, if I kind of look at the traditional, like if I go like 10 years earlier, primarily people kind of doing the storage allocation like this. So in your company, you would have maybe some kind of a SAN storage, which will be from like EMC, Hitachi, and so on. And then as a user, if you require a storage, you will kind of talk to that instance, what you have. That instance is going to have something called HBA, or hardware bus adapter, or an FC thing, something kind of stuff there, in which you kind of do a one-to-one connection between the storage and the VM, and that's how the storage is given to those uh, machines there. So you have a sense or kind of NFS kind of storage where you will carve out the storage. When I carve out, kind of say I want 10 GB or I want 100 GB, whatever. The request goes to the send, and then the storage comes back to you. But this kind of storage is very expensive. So if you kind of, it might go in millions as well, right? So if you kind of look at the pricing of these storage, you'll be surprised that how much these storage array would cost in dollars there. So over the time, we kind of saw that, okay, instead of going over with the slide of big SAN storage, why not we can kind of take the community hardware and then pull the storage from there. So like here, what you're seeing that I have 3 hosts, and suppose all of my host has 100 GB free, I can pull all the storage and create a 300 GB volume, which is available over the network. And as I request 100 GB, whatever the size, I can go and talk to this kind of a say pooled storage and carve out my storage of 100 GB from there. So example for these are like cluster FSF are the examples of this, where you can basically carve the storage and assign it to the machine or the bare metal, whatever you might have. Then of course things are changing, and then we kind of now move to the container world, where we have orchestration like Kubernetes, and on that we run container with the help of pods. And then we want those containers to have a storage, because containers are available by design. So if container goes down, the data stored in that container also goes with it. So what you need is you need a way to attach a storage from somewhere, right? That somewhere in typical sense, what we have, like again, we can have again SAN kind of stuff, or let's say we have our SDS like cluster.fs or self-configured from somewhere. We can get the storage, connect to our instance first, and from the instance we can then give it to our containers there. And you would have used multiple times. For example, if you configured a cluster on AWS, for example, you can get those EBS volumes attached to your instances, and then from there containers get the storage. And you would have used PV and PVCs to kind of do that part for you. What's kind of emerging now is why not we can have storage in containers. So one is storage for containers, that typically we know how to do it. You kind of get the storage, connect to the instance, and then give it to the containers there. That's one way. What's emerging now is storage in containers, in which the storage is deployed inside the container along with the application. And then it can be orchestrated by the Kubernetes itself. So I know this might not be very clear now, but as we continue, you kind of see this pattern. And it is very friendly to the dev and admins, because you are orchestrating within the Kubernetes thing. And if you know how to orchestrate in Kubernetes the applications, you can orchestrate the storage as well. So I'll answer this question, this kind of things in detail. So if you have any questions on this one, we can just take them in some time. So in Kubernetes, of course, we have volumes. You would have kind of used that one. So here we have a pod. In pod, we can have a volume, and each container in the pod can decide where they would like to mount the volume. And there are these volume providers you have, like AWS, or Elastic Block Storage, cluster.fs, host path, local NFS, and so on. So you have different drivers for your pods there, right? But the problem here is this is like a kind of an extra burden for a developer. If I want to use, let's say, storage on AWS or on Google Cloud or whatever, my developer need to kind of go and talk to my cloud provider first, create the volume, and then come back and consume it. So that a developer need to kind of take care of the volume creation first of all, and then consume it. So the developer might say, I don't care. As a developer, I just want to have a storage. Why you're asking me to kind of go and connect to any cloud and do that? Similarly, it is not very friendly for our ops person, right? Ops is not going to give the cloud access to every developer. So the volumes are there, but not kind of used primarily there, because not developer, not your admin would be happy with that. So what we have done in the next level of implementation of Kubernetes, we kind of decoupled the volume creation from the volume consumption, right? So what happens in a way, My developer just kind of creates a claim. So saying a developer says, I want a storage of 40 GB, something like that. And he would just kind of stick with that. The developer is not kind of responsible for doing the volume creation on the cloud or wherever it is. That is the job of my administrator. So what happens in this case is my administrator would create some predefined volumes ahead of time, right? So in advance, it's done by administrator. Like for example, the developer might have created a 10 GB volume on NFS, 50 GB on AWS, or 100 GB on ISKZ, whatever it is, right? So I have pre-available volumes with me, which I want to kind of use, which I can use down the line. So admin has finished his job. Now the developer kind of comes and say, I want a storage of 40 GB, right? So that's what the requirement what developer comes with. Now here I have 10 GB, 50 GB, 100 GB, but there is no exact match of 40 GB. So what will happen is I'm going to kind of get attached to the 50 GB one, right? So my developer though requires a 40 GB, but I'm getting a 50 GB one, which means there is going to be 10 GB of fragmentation because I want 40, I got 50, I don't care about 10 GB. Similarly, if I had like 130 and 110 GB volume, I cannot merge them and make it a 40 GB and give it to my user packet because my volume size are very static there. So these are called as static volume provisioning, in which your administrator has created volumes ahead of time, which you are going to kind of consume. But I think the problem is very clear. The fragmentation is there and you can't merge it. For example, if there has been no 50 GB one, you would have got 100 GB one, which is like 60 GB of waste, right? And if you have, let's say, if you had like 10 GB available, you can't merge and make it to a 140 GB one. This is the static volume provisioning. So then to overcome that, we kind of created this dynamic volume provisioning in Kubernetes, in which my developer requests again the same 40 GB one, but what's now happening is I have created a called storage class. So when configuring the Kubernetes cluster, the administrator of the cluster would choose a storage class to consume or kind of to create, and then use it for my PV creation. So like for example, I give an example here. So here I have, let's say, not Docker. So if I do a kubectl get storage class, as you can see that currently I have a storage class called rook-sef block, right? So I'm going to now request. So when I'm going to create the volume with the help of PVC request, I would request that PVC or the storage class which I have in this rook-sef block, and this is going to give me the 40 GB storage on the fly. So I'm not creating any PVs ahead of time. So if I look at kubectl get PV, there's no PV currently there. But as I'm going to request, I'm going to get that PV created on the fly as the request comes in. So I would need to have the right storage class configured on my Kubernetes cluster. And I can have multiple storage classes. Like for example, I can have a storage class for the slow storage. Then I can have a fast storage class with the SSD in the backend. And then my developer can choose it would want a slow or fast storage, and depending on that, I would get the right PV. Right, so that's there. So we saw that volumes, static volume provisioning, dynamic volume provisioning. Yeah, so people are asking question about there. So we are already live on YouTube. So it's available on YouTube down the line. So don't worry about that recording part. Right. Okay. So then we have the extent. So what happens now is you have the storage class, but then there can be multiple providers also, right? So like for example, the storage can come from EMC, Cisco, or whatever. There can be different companies, and then there can be different SDS like Ceph, GlusterFS, and so on. So there are so many providers are there, and then there can be new entrants also. So what we want is a way so that people can extend Kubernetes storage on the fly, right? For example, if I'm creating a new storage plugin, I want to have it in the Kubernetes. So what I could do is I could kind of create these out of tree storage extensions and put it to Kubernetes on the fly. So for example, I'm a new company. Let's say Cloud develops its own storage management, right? What I could do is then I could go to Kubernetes and then I can insert my plugin on the fly. And that is possible with the help of container storage interface, which is there in different container orchestration softwares, which gives you a standard way of attaching the storages. So you have a Kubernetes cluster which would have CSI installed. Then you can kind of bring in own storage plugins and install on the fly on the Kubernetes cluster. And that's how different companies are building these storage software. And that would work seamlessly in any Kubernetes if they have cleared that conformance test and so on there. So there are two ways of doing that. One is a flash volume, which is deprecated, or there is a CSI. So I think what you would see that, okay, as of now, things looks perfectly fine, right? Why do I need an orchestrator on top of this for the storage, right? Because I have static volume provisioning, dynamic volume provisioning, all that stuff. That solves my problem. But why would I kind of care about, again, orchestrating the storage on Kubernetes? Let's talk about that now. So what's missing as of now, right? So if you look at the volumes are still managed outside the Kubernetes. So if you kind of get an EBS volume, that is again on the cloud side, right? And you don't kind of control much of that stuff. Then there can be difference in the parity between the cloud providers. So for example, today you are running a Kubernetes cluster on AWS, then you want to go to, let's say, Google Cloud and so on. And their storage management is different. So the way AWS manages storage is different than the storage management by Google Cloud, right? So there can kind of a conflict can come here. Similarly, the parity is not there between on-prem and on the cloud. So on-prem, you might not have that same storage class of AWS, right? You would have on-prem, let's say, Rook 1. So how would you kind of do those kind of stuff dynamically? And that's where the orchestration of the Kubernetes storage would come in place. And we kind of also call that as a hyper-converged storage system with Kubernetes. So what you're seeing here is I have a Kubernetes hardware, which can be VMs also. Then I deploy Kubernetes along with some kind of software-defined storage and then software-defined networking. So it truly becomes a hyper-converged environment. And then I would have applications which can have multiple pods. And then those pods are going to kind of connect back to your SDS or networking and so on. And that's how they work together. Hyper-converged means you have storage, compute, and network together. And dynamically you can provision them on the fly as requested. So this is typically what we meant by storage orchestration with Kubernetes, in which you create a complete hyper-converged storage environment. How do we do it? So we do it with the help of container attached storage. So I was telling you about that. This is the container storage in the container. So what happens in this case is you would again have the typical storage on your VMs or on your bare metal, whatever it is, right? Like it can come from the local disk, or it can come from AWS, Azure, and so on, or it can be a SAN from there as well. So that is attached to your instance now, right? Now what we have here is, again, the PV and the PVC concept remain same. You have a pod is going to request a PVC, and then we'll have a PV. So this particular thing also is same, right? But what we have changed now is we have kind of created a container attached storage here. So what happens in this case, the container what you're going to create, these are going to be further containers or the pods there, which are going to have the storage blocks along with that, right? And you will have a controller pod and the replica pod. So in any CAS system, you would kind of deploy the CAS pod, which would have somewhere to connect the controller and which would have a replication of the data depending on how you've configured. So you're going to kind of create these CAS pods on demand, and you can have the policies based on the requirement. So for example, if you are deploying a database database like for the MySQL or MongoDB, whatever it is, right? And you want and higher, faster storage for that. So in that case, you will kind of create the CAS accordingly, and then you can put the custom policies in place. So for example, you can say that I want to have this particular CAS to have certain policies, like I would get X amount of IOPS on that. So all those granular information you can kind of pass on to these caches. So cache is going to create these, or cache in general is where the pods which has the data along with it, and it goes along with the app. So wherever the pod is running of your app, the cache get attached to that one only. So that the locality of the data is very nearby, right? So you kind of, the pod can directly access the cache attached to the nearby node itself, right? On the same node itself. That kind of makes your access very fast there. Also, with the help of cache, like for example, if I take an example of, let's say, OpenEBS or Rook and so on, whatever it is, right? So now I can be a cloud agnostic. So what I meant here is you have these nodes here, or the Kubernetes cluster. These Kubernetes clusters are created on AWS, Azure, or on-prem. And instead of using the direct AWS connection there, what I'm doing is I'm going to kind of deploy this cache layer in between. And then my Kubernetes is going to communicate with that cache layer. That cache layer is common for me, irrespective where my cloud is. So my cache layer, let's say OpenEBS, right? So OpenEBS running on AWS, OpenEBS running on Kubernetes on-prem, Kubernetes running on Azure. So my Kubernetes pod or the volume requirement goes to this cache, and then cache then kind of have at the backend maybe an EBS volume attached to it. So that way, my kind of request is going via cache as an intermediate layer. So I don't care where my cloud is running, because my volume management would be very common because of the cache layer there, right? So what happens, like, so for example, if you are running a cluster of 5 nodes today, and then you kind of fill up all the storage and so on. So with the help of cache, you can just, in the case of cache, you can just add more nodes. And as you add more nodes, then you can create more pods. So with that kind of, you can scale out on demand as you kind of request. So you need to kind of take care of the storage provisioning ahead of time. You can scale on the demand. Right? So what are the benefits of the cache there? So first of all, it is a microservice-based architecture. So as you know, in the microservices, right? Things are very kind of small, right? And then you can kind of work on them or update them on demand and so on. So all the microservice-based feature you will get with the help of cache. Upgrade becomes very easy. Backup becomes very easy. Those kind of things become very easy if you kind of use this kind of an architecture there. And orchestration already taken care by Kubernetes. So it's not that you need to kind of write a separate orchestration software just for storage, because those are typical pods you are running. So we can orchestrate them with the help of Kubernetes. Of course, depending on the cache software you're deploying, you would have a respective CRDs for that. CRDs are custom resource definitions in Kubernetes, using which you extend the Kubernetes cluster to something else. So if I'm deploying a software, for example, Rook, then I would have the Rook specific CRDs on my cluster. And now after that, my bottom unit becomes pod. And then we can orchestrate that thing with the help of Kubernetes itself, right? You can avoid logins because of cache layer, right? Because I told you earlier, you can be in any cloud, your intermediate layer is cache layer there. You can easily scale, just add more nodes, you can scale on the fly. It is very developer and admin friendly, because again, you are working on, so developer and admin both working on the pods. They kind of know how to kind of handle deployment and so on. And this kind of becomes a normal, like a common workflow for them, instead of they have to learn something separate. So once you deploy that cache software on your cluster, the developer and admin kind of just play as another pod there. You can apply policies on those pods or cache separately. So you can kind of easily divide the kind of workloads you have and what kind of policy you want to put in. Like, I want to have different IOPS for my specific app. I want to have higher priority for all that stuff. That's all possible because of cache there. And then you can have lower TCO, because you are actually going to use the hardware watts, or the storage comes with the storage, the VMs only. So you already have VMs, and you're kind of just putting that software on top of that. But of course, you're going to add more storage like from EBS and so on, but that's going to be much cheaper as compared to using some separate storage altogether. And you, as you scale on demand, you're going to save a lot of money in that one. This kind of benefits you can have with cache there. What are the examples for the cache there? So Longhorn, OpenEBS, Portworx, Storage OS. So these are different examples of different kind of cache implementation there. So they all use, but there might be slightly different the way they have implemented this one. So I'm not going to kind of go and dig deep into each one of them because that would kind of run over time, and then I think it's not part of this particular session though. So I'm going to give a demo of Rook quickly. So what I have here, I have configured a Kubernetes cluster, and in the Kubernetes cluster we have deployed the Rook. So if I look at kubectl get CRDs, so as you can see that, okay, so with the help of Rook, we can create different kind of storage. Like if you go to the Rook's website, you can see that it can orchestrate different kind of storage like Ceph, object storage, YugaByte, EdgeFS, and so on. So currently I have configured the Rook to kind of orchestrate my Ceph. So with the help of this, I can orchestrate my Ceph clients or my Ceph on those nodes. So for the demo purpose, I'm going to quickly show you that currently the storage class we have configured here is Rook Ceph block because of that Rook installation. And then I'm going to use Helm to deploy a state or like a stateful application, or maybe it's an application that kind of consumes some volumes and would require some persistent storage for that. For example, Jenkins or MySQL or whatever it is. So let me let's search for, let's say, Jenkins here, or I can search for MongoDB, whatever it is, right? So let me just search. So as you can see that I have this MongoDB here. Let me just install that one, and this would definitely want to create some kind of PVCs request, and those are going to be served by my Rook Ceph running there. And as you can see that it is going to kind of just maintain. For example, let me show you here. If I do a namespace, kubectl get pods -n. So what Rook has done is it is kind of orchestrating the Rook behind the Ceph behind the scene. So as you can see that there are some kind of Ceph components running as pods on my different nodes there, like Mon, operators, manager, and so on, OSDs. So my Rook is going to communicate to the Ceph behind the scene or the Ceph pods behind the scenes and request those Ceph pods to create the storage for me and give it back. So I am not going to touch anything on my nodes per se, but I'm still going to get those volumes on the fly. And that's possible because of what I've shown earlier. So let me go ahead and install that Helm package here. So I'll install DB. If I just do this one. So it's been deployed, and if I look at kubectl get pods now, or let me look at get pods. Since they're doing an init now, and if I do a get PVC, you see I have made a PVC request, and it is bound to a PV here. Correct. So as I'm going to create more of these replicas, I'm going to get more PVCs and PV created on the fly. Again, I'm not kind of managing them myself on the nodes, right? These are managed by the Ceph pods running via the Rook there. So Rook is an intermediate layer. Kubernetes communicate to Rook. Rook would take my request to the pods of Ceph, and they'll kind of take care of the volume creation and so on. So yeah, let's see more PV and PVCs. Yeah, as you can see that I'm getting more PV and PVC getting created, and they're kind of attached to different. So my PVs are getting attached to the PVs there. So demo we have already seen. Let me see if there are any questions on the chat now. So yeah, as an end user or admin, how does it help having CAS if I have CSI of various cloud? So I was kind of mentioning about that. You can definitely have a CSI for different cloud providers, but if you want to have a cluster which is, or you have multiple clusters in different environments, Gautam, like on-prem, on cloud, on you want to connect them together. So then your workflow remains same, irrespective of whichever cloud you would go in, right? That's one thing, and you can kind of use the local storage also if you use CAS. For example, like in our current scenario with what I have configured, I have not used any storage from the cloud like EBS and so on to get the underlying storage for my CAS. My CAS is actually coming directly from the host machine itself. So that kind of helps me there. Hope that answered your question. For enabling the CAS, is it straightforward or we need to have an OS level changes? Nothing is required in that one. You just need to kind of, again, it's the kind of a say, as I mentioned that, right, this CAS software comes as the CRDs for Kubernetes. So it's like deploying any operator or deploying any CRDs on the cluster. So you just kind of go pick up the right, let's say their YAML files, and then just run on the cluster, and they will take care of the things there. So CAS is like a Kubernetes component which has its own pod. Yes, correct. That's right, Gautam. Any more questions? Recording definitely we'll have. Okay. If no questions for me right now, we can just get on with Nikhil there. And if you have any question for me, you can just feel free to kind of comment on here, and I should be able to kind of answer them maybe after the post Nikhil session. So let me just unshare my screen and let's have Nikhil to kind of take over now. Yes, Nikhil, all yours.
Perfect. Let me find the presentation option. Share your screen. Let me know if you're able to see my screen.
Yes, we can. Carry on.
Okay. Cool. Thanks, y'all. Thanks for joining. My name is Nikhil Chandrappa. I work as a lead software engineer at YugaByte. So I kind of work in the ecosystem team where we kind of build integrations with other products like Kubernetes, Cloud Foundry, and also I work on the database drivers, Spring Data support, as well as the GraphQL support for YugaByte. Prior to this, I was a senior data architect at Pivotal. I did the whole 360-degree from big data, in-memory data grids, cloud-native databases, cloud-native pipelines, and things like that. So I've been working in distributed systems for quite some time now. And I'm originally from the area that Nipendra is from. Like, I'm from Mysore. So this has been great that I was able to participate in the meetup. So before I actually get started with the distributed SQL concept itself, right, I just wanted to give a brief overview of the current state of databases in Kubernetes, right? Like where we are at and things like that. So we all know Kubernetes has been like super popular in Fortune 500s as well as startups, right? Like a lot of people have started deploying their workloads on Kubernetes. So one thing that we see on the screen is like these are like some of the like largest e-commerce applications that are out there. One thing about e-commerce that we need to understand is the traffic pattern for all the e-commerce applications kind of it does not remain the same throughout the year. Like situations are months where there is like a Black Friday sale or a July 4th weekend or like a Diwali sale, right? There's going to be like a lot of spike in their traffic, and also they need to have like a platform which kind of supports linear scalability, like seamless scaling, and also be able to provide like 100% of uptime for the whatever the SLAs they have for their services, right? So and Kubernetes kind of simplifies all those things for like devs and app developers otherwise. So that's why all these companies have started adopting Kubernetes, right? So it all started with like developing stateless applications. Now slowly and steadily there has been like a lot of push for enabling stateful applications and databases as Kubernetes itself matures. So Kubernetes data services ecosystem is kind of rapidly evolving, right? Like these are like some of the popular ones out there, like Cassandra's, Mongos of the world. So back in 2017, when I was at Pivotal, we were working with DataStax, Confluent, and all these people to build operators for Pivotal Container Service, which is a managed Kubernetes offering from Pivotal back then. So during that time, it was so hard to build a database, like orchestrated database on Kubernetes, right? Like we didn't have stateful sets where we had to rely on replica sets, and it didn't support rolling upgrades, and volume provisioning was hard. We had to manually do it, bunch of things. Like as Kubernetes is maturing, right? We kind of are seeing a lot of database vendors started to offer their database on Kubernetes. So in this presentation, we are gonna mostly concentrate on how distributed SQL with Yugabyte works and how we are orchestrating that distributed SQL on Kubernetes. So these are like some of the advantages that we see for data services when moving to Kubernetes. Obviously, like Kubernetes is a really good resource manager. It kind of helps you to better utilize a cluster. You can support multi-tenancy, which means you can have multiple different database clusters running in the same Kubernetes environment in different namespaces, so that they have multi-tenancy and everything built in. But one of the important things that actually helped a lot of database vendors is the adoption or the maturity of CRDs. CRDs helps us, like the custom resource definitions, helps us to build a lot of uh, really good day two operations with your database, like your backup restore, when you had to take backups, and monitoring, bunch of things like that. It becomes super easy with CRDs. And as the operator concept in Kubernetes is evolving, all these things kind of given a path for enabling data services on Kubernetes. So a brief about YugaByte. YugaByte actually is a distributed SQL database. It has its roots in Facebook. So a lot of the co-founders of YugaByte were some of the main data engineering team that actually ran Facebook's Messenger and Wall from 2007 to 2012. Like if you see the scale that they were running it from, like, or this the scale that they had to manage, like from 50 million to like a billion users. So they were the ones who came up with or incubated the Cassandra and HBase database in Facebook. And one of the co-founders of mine, Karthik, he came up with the term Cassandra when he was at Facebook. And also, a reason why I have Oracle is one of the other co-founders of Yugabyte. He is like an industry veteran. He has 25 years experience in Oracle, building the core Oracle DB engine. Like some of the code he has written is still used in Oracle engine. So what they thought was they wanted to bring all the experience they had in a net new database, which actually has like all the goodness and all goodness of a RDBMS system, and also be able to massively scale. So that they want to bring the best of both worlds and create a distributed SQL database. So distributed SQL supports global transactions, and also it supports global data distribution. When we do sharding of a relational data, obviously like things like HA and fault tolerance will be built into the product. Uh, Yugabyte, we kind of call Yugabyte is like in a distributed SQL terms, we kind of fit into this category where the SQL or your relational workloads, you can have high performance, like low latency reads and writes, and also it is cloud native. So when we say cloud native, for us, what that means is you can easily orchestrate your databases on any infrastructure that is given, like whether it's your public cloud, private cloud, your data centers, and platform of your choice, Kubernetes. If anything else comes down in future, we should be able to support that. So things like traditionally databases are always like single node, right? Some of the things like HA and fault tolerance are built in later into the product. So for us, with distributed SQL, like HA and scaling were the core characteristics when we were incepting the product itself. And also at heart, Yugabyte is the 100% open source. So we took a decision back in 2018 to make YugaByteDB itself, YugaByteDB fully open source. So we welcome any and all contributions if you guys want to do it. So I'll share the link later on. You can join us on our Slack, our community, as well as see the issues that we have on our GitHub. Uh, and obviously, we are not the only players in distributed SQL, right? There's like a few other big established databases like Amazon Aurora and Google Spanner. They also fall in like the distributed SQL category. So Amazon Aurora, if you have not seen, it's like one of the fastest growing data services on AWS. So the reason being, it provides fully RDBMS features, and also it's able to support HA. But Google Spanner took a different direction where it was one of the first horizontally scalable and strongly consistent globally distributed database based on the RAF consensus algorithm, and it kind of drives all the Google ad business and bunch of other things inside Google. Even now, you can as a developer, we can use that on GCP as a cloud spanner. But one thing they did was they couldn't support the entire swath of RDBMS features. So things like foreign key relationships, all those things doesn't work with Google Spanner. They had to come up with their own new SQL syntax. So this kind of takes developer job. It makes it much more difficult, right? You have to create all new syntaxes. The migration story will be much harder. Uh, However, Amazon Aurora, since it's MySQL and PostgreSQL compatible, it is very easy for us to move to Amazon Aurora compared to Google Spanner. So that's why Yugabyte kind of got inspired by these two databases, and they wanted to get all the Postgres compatibility with the distributed SQL nature that Spanner supports. So we were able to do that with a layered approach. So what I mean by that is we have two layers. One is the DocDB layer. DocDB layer is the one which is responsible for sharding the data, providing geo-distributed transactions using RAF consensus protocol. On top of that, we have the query engine, the pluggable query engine itself. Currently, we have two APIs that we support. One is a YSQL API, and another is a YSQL. YSQL is a fully relational SQL API that is compatible with Postgres. YSQL is more like a NoSQL kind of API access. It is Cassandra compliant. So depending upon your access pattern and the use case, you can go ahead and use either of those APIs. It makes it super easy for when we are developing cloud native apps. Like we're going to see this further in the presentation when I'm going to touch about like a real world example. Cool. And one thing, if you see about Yugabyte cluster is in a Yugabyte cluster, it doesn't matter how many nodes you have, like all the nodes are identical. Like based on the architecture I talked about, you have a query layer and a storage layer. And any microservice any microservice or any app that is connecting to the Yugabyte cluster will have same access, like it can connect to any of the available nodes, and it can do reads and write. We have built some intelligence into our client drivers, like with YSQL driver, it is cluster aware and topology aware, and we want to bring the same intelligence to the JDBC drivers also. So the current JDBC drivers are like, it doesn't understand clustering, right? It is like always connecting to a single node. Like even if you see the Postgres connection string, there's no way that you can specify like a list of coordination nodes or like a seed nodes that we need to discover the cluster. So all those things we are bringing to the Postgres JDBC driver. We kind of forked the Postgres JDBC driver so that we can get the cluster and topology awareness into that, so that it is easier for the applications also to scale. You don't have to maintain like a load balancer on top of your database. If we double click little bit inside Yugabyte cluster itself, so Yugabyte as I said, Yugabyte made a kind of scales using a sharding methodology. So we usually we call it as a tablet. So Yugabyte, any table, as soon as you create a table inside Yugabyte, it kind of gets sharded into all the available nodes. One thing you see here, there's like two kind of processes that we run. One is called as a T server. That is the one which actually maintains or holds all the data, and master is just a coordination node. It is only responsible for like whenever there is a leader consensus election happening, like a RAF consensus election happening, that's when it takes place. Otherwise there is no traffic that's going to go into master. So all the traffic and all the data actually goes through YBT server. And if you see in the each tablet, which is a shard, have additional copies of data sitting in the cluster as well. So which means like most of the Yugabyte clusters or the distributed SQL clusters have redundancy built in into the database. So most of the times developers use like a RF3 cluster, which means a replication factor of 3. That means you'll have one primary copy and two secondary copies, or one leader and two followers. One thing about YugaByteDB, since we support truly consistent database, as soon as a transaction or as soon as you write a data into like say shard leader, it automatically it automatically writes to all the other followers as well before sending the acknowledgement to the client. Hence the entire data set is consistent. Doesn't like, even if you lose your primary node where the primary tablet was running, so the other two nodes will still have the consistent data. There won't be any data loss. So that's why that's how we are able to bring in that's how we are able to bring in scalability, as well as still still get the required consistency for running operational databases. In now coming to how we are scaling the Postgres SQL itself using Yugabyte, like obviously Postgres, we are reusing the upper half of the Postgres layer, just replacing the storage layer with our DocDB storage layer. So whenever a query is fired from the client app to any of these YSQL query layer, any of them can accept it, and they're gonna distribute the processing to all the other available nodes, so that in an essence we are also benefiting from the parallel processing of the data. Like the storage layers will only work on the specific data set that it has, and it sends the result back to a coordination node where all the results are kind of combined and sent it back to the clients. So this is kind of a parallel processing we kind of do, so that we can have high performance and low latencies that we support with YugaByteDB. Any questions so far? I know I've introduced quite a few concepts.
There are a few questions on the chat if you go there.
Yeah.
Something about this would this will slow down things. Something about that one. Uh, yeah, you can just kind of take them.
Oh, okay, 1 second. ML cockroach DB, what will slow down things? So yes, it was actually inspired by Google Spanner. Google Spanner came out with the RAF consensus algorithm, right? So we actually took that same RAF consensus paper and we modified the DocDB, which is based on a RocksDB, and there's like a bunch of other things that we built as part of that as part of that update we did, where wanted to support multi-row distributed transaction using Raft and things like that. So that's where most of the engineering effort went into it. So yes, CockroachDB and YugaByteDB are competitors in the distributed SQL space. Hope that answers the question. Cool. I'll continue. Okay.
So there's one question. There's one question from the YouTube. I just put them in the chat here.
Yeah.
If you just answer that.
So we do support both APIs. Like it is schema based, which means like we support relational schemas as well through one of our YSQL API. so which is a fully relational API which is Postgres compatible. And we also support NoSQL based, which we call YCQL, which is like Cassandra query language compliant. So it is not a multi-model per se. What we do support is like multiple APIs for storing against your database engine. So that's what we support. So if you know the difference between multi-model, like Cosmos is a multi-model, you kind of write the data once and it kind of stores it in different formats, whether it's SQL, NoSQL, or a graph database. So for us, we fall in the multi-model category. It's just that we kind of support two different APIs where, depending upon the data set or the use case that you have, you can go ahead and use either of those. So hopefully that answers the question. Cool. So when we said we are cloud native and a globally distributed database, right? Uh, we have like a few deployment topologies we support. So one is like in the if you want to deploy your cluster if you want to deploy your database on multi zones within a single region, we do support that, which kind of avoids zone failures or rack failures if it's in a database, if it's in data centers. And also we support multi-region deployments. So even if there is a region outage, your data will still be consistent because we support consistency across regions as well. And whenever the apps which are connecting, it can seamlessly fall over to the region where the data is and read the data. So that's why the business continuity will be there when you are deploying across regions, and when there is a region failure or a data center failure. And also we do support multi-cloud, which is for globally distributed apps, or this is kind of very popular in enterprises where we kind of see a pattern emerging where you have two copies of the data in your data center, and you want to have the third copy in a cloud for HA, or kind of augment your storage capacity using a public cloud offering. So this is a new hybrid cloud or a multi-cloud deployment strategy that we are seeing widely being used in the industry, and Yugabyte kind of seamlessly supports your data replication on all these in all these topologies as well. As I said, there's been a push in the industry, and a lot of architects are started to think about deploying their apps globally, right? So if you see Spotify's of the world or Amazon's of the world, where they want to have a highly available data tier as well. So for deploying applications on let's just say multiple locations is already being done, right? Like now we can have the data also reside in a place with so that it can reside in the same place where the apps are, so that you have one, you'll have better user experience. Second, you have business continuity when there is an outage, like a region outage, entire like say all the databases in or all the data centers in US went down or Asia went down, you still have business continuity. And also it is useful for geo partitioning and geo replication. You can load the data in one location and it kind of distributes in all the other places. And also sometimes it can be used for data compliance. So that's where we see there is a fit for distributed SQL, and databases like YugaByteDB come in. So next, I'm gonna quickly show you how we orchestrate Yugabyte DB on Kubernetes. So before I go there, any other questions on the Yugabyte concept itself? There's like only few things that we have to know, like the T server and master. Those are the main two components in a Yugabyte cluster, which are responsible for the cluster coordination. I'm going to show you how we provision storage and how we provision our pods and things like that next.
So there are questions on the chat screen there. If you can just take
Okay,
them.
sounds good. How is the query execution happening multi-region? Does it happen on all nodes? So that's a very good question. Let me go back to my screen here. So if you see here, the query execution, the query, whenever application like fires the query or submits the query, right? That actually goes to a node which has the primary leader or the raft leader for that particular table or that particular data set or tablet. So and then it kind of does a distributed push for the subqueries. We call it as push downs into our docdb layer. And then whatever the main node which got the query first, that acts as a coordination node. All the other nodes kind of compute the result and send it to the coordination node, which sends the result back. So that's how the query execution works with Yugabyte. And also we have a concept where we can select in a multi-region or a geo distribution deployment. We can specify something called as a primary set of nodes, or we can consider them as a default nodes. Like all the writes will go there, and all the reads will go there. So that's something that we use whenever there is a latency, when there is like a low latency requirement applications, right? We kind of make one region as the primary and the other two as like the secondary ones, and all the writes and reads goes to that region so that the transaction is faster. Is it possible to give a brief about migration from Oracle to YugaByteDB? So migration from Oracle to YugaByteDB will be same as migration from Oracle to Postgres. So we are a Postgres compliant database. Like most of the features that are there in Postgres, we do support, and there's like few ones which aren't supported, like save points and few other things. So all those things we are working towards getting there. Uh, and like if there are any migration tools out there which supports Oracle to Postgres, that tend to work with Yugabyte as well. How many data nodes maximum that it supports? So it's we have tested more than 100 nodes. There is no limit to it. The limit actually becomes CPU sometimes, because this RAF consensus protocol, right? Like all these shards that we all the shards that we create for a table, so each of them need to undergo a RAF consensus election to determine which are leaders and followers. So it's gonna so more of the it is not really like number of nodes. It's basically like the CPU utilization itself. So we have scaled Yugabyte to terabytes of to hundreds of terabytes. So petabytes is something that we are working towards.
So, Akhil, so there are two more questions there, Nikhil, earlier to this one.
Yeah,
So, is if you just go up, a few of my discussed things there, right? So, there are questions about how does Gigabyte compare with Cassandra, and
correct,
then is the schema based like have been already answered? Right? So,
correct. So for Cassandra, Yugabyte YCQL component is Yugabyte YCQL is Cassandra compliant. The way that we work is Cassandra, the way the sharding works in Cassandra is different to the way the sharding works in Yugabyte. Cassandra follows token-based murmur sharding, right? So we support, we have our own consistent partitioning that we do using our own partitioning metadata. And also one thing that we support that Cassandra cannot is like we support secondary indexes and secondary indexes with YCQ and globally distributed transactions, so that the data is consistent. So with Cassandra, those things are like super slow. Like when you want to have a highly consistent reader, right? So with Yugabyte, that's not the case because we don't follow the token topology that they do. Okay. Is there any other questions? Okay. extra layers, a leader push down retrieval. Will there be any cases of lockdown of tablets or data loss or timeout issues? How to handle that? So that's a really good question. We have bunch of timeouts that we do internally as well. Like if a query doesn't return within 60 seconds, we kind of cancel the transaction and ask the user to do a retry. So there's like bunch of those things built in into the system, like kind of guardrails, so that it doesn't go into a deadlock loop or like an infinite kind of a loop for retrieving the data, or situations where you kind of do a select star on $1 billion, sorry, on a billion records, right? You don't want to like send all those data back to the client. There are like situations where we kind of limit the things that you can break the system. So that's how we kind of have guardrails around like deadlock and with push downs. So as and when we keep pushing down, and if the push downs doesn't return in a certain timeout, we cancel the transaction. I mean, we cancel that query, cancel the push down itself. Oh, some really good questions. Thanks, guys. Thanks for those. Okay, where was I? I was going to do if there aren't any more questions. Correct. Uh, if there aren't any more questions, I'm gonna continue with the presentation. Okay, perfect. So, as I said, YugaByte, there's like quite a few ways that we can deploy YugaByte on Kubernetes. You can straight deploy YugaByte as a stateful set. We support Helm charts. We do support a YugaByte operator, and we have another way that we orchestrate using YugaByte platform. So YugaByte platform is kind of YugaByte platform kind of automates all the day two operations for us and provides a really good way of monitoring the system and bunch of things like that. So we are gonna today see how YugaByte orchestrates a database on Kubernetes using our platform, right? So this platform can be used for deploying YugaByte across like any database, any cloud providers of your choice or Kubernetes of your choice. So this is the portal that we have deployed on Kubernetes. It also runs as a pod within Kubernetes. It's just a single pod. If I go and show you my Kubernetes cluster, what I've already done is I went ahead and I have deployed uh, deployed this YugaWare cluster. We call it as YugaWare internally, which is nothing but the YugaByte platform. I've deployed that pod, which actually is responsible for provisioning clusters on Kubernetes itself. So we kind of we kind of envision this as supporting database as a service on cloud provider of your choice. Now, so you can specify configurations for any of the cloud providers you have, and also on the on-premise data centers. So on-premise data centers, right? Like doesn't matter if it's AWS, Google. All you have to do is specify the configurations, and once we know the config, we can go ahead and select the uh, IaaS provider of your choice and deploy cluster there. So for today's work, what I have done is, since I'm using GKE as my cloud provider, I went ahead and configured kubeconfig for GKE, and I will use that configuration to deploy the clusters. So if you want to see a real world, a real situation, or a real how we envision our a lot of YugaByte users using the YugaByte platform. This is how we kind of envision them to use. Like this is one of our dev portals where we have like bunch of these clusters that are currently running and is managed by YugaByte platform. And if you see here in the world map, we have configurations for starting up clusters in bunch of places. Like say I can go ahead and start a cluster in Asia Pacific, or I can go ahead and start a cluster in Asia Pacific, Tokyo, India, and also a bunch of other places in the world, right? Like this is how it works. Like if I go and start creating a cluster, I can select a bunch of providers. Like say I'll say GCP provider, and in the region, oh GCP, okay, I'll do AWS because we other regions. So if I say AWS provider, I can specify Asia Pacific Mumbai. And if you see here, I'm saying in I want to have two copies or two nodes of my data go into South 1A and the other in South 1B. This is like a deployment topology where I'm deploying the cluster on different availability zones. So if I want to deploy on different regions, let's just say I want to deploy it on Asia Pacific Tokyo. So now if you see that two of my if you see my nodes are gets distributed across Asia Pacific, Mumbai, and Tokyo. This is how we are able to very quickly and easily deploy YugaByte clusters on different regions. So there's like a bunch of other things we can configure, like the instance type that you need for each of your cluster and what is the amount of volume you need. And we support GP2, IO1. This is since this is a VM based, so these are the EBS types we support. And you click on create, it just goes ahead and orchestrates the database for you. And let me show you one of the live clusters that we have. A few things about the live cluster. So it actually shows you the bunch of metrics as well. Like if there's a workload running, you can see all the metrics that are currently being put out by YugaByte cluster. We kind of use Prometheus behind the scene, and you can use a Grafana database if you want to have like some alerting and things like that. So let me get back to my Kubernetes-based platform, Kubernetes-based platform, where I'm gonna go create a cluster now. Let's say, let's call it a demo cluster, and I'm gonna choose one of the fast SSDs that we have. Like you can specify different types of storage classes when configuring the storage provider, similar to what Nipendra told us, right? There's like a bunch of ways that we have done. Right now, I have a CSI based fast SSD for GCP. In future, we can have a container attached storage using Rook or something, Rook as part of our platform also. Today we don't support Rook on our platform, but we support a Rook based operator for YugaByte. So I'll select a fast SSD, and for now I just have a US East region. And if you see, this is a single region, and and everything gets deployed on the same availability zone. So I'm gonna say one of the extra small, so which means that each of my pod will be of 2 vCPUs and 4 gig RAM. And I want to enable relational YSQL for relational workloads. And let me quickly reduce the reduce the volume size because it's a test cluster. We are using for demo. So all I do is just say click create, and it goes ahead and starts deploying the stateful sets and required PVs and PVCs. It makes all those things behind the scene. So let me quickly show you what's happening behind the scene. Each of the YugaByte cluster gets deployed in its own namespace. So for based on whatever the name we gave for the YugaByte cluster, like YB dev demo cluster minus watch. So if you see each of the first thing that comes up are the masters. As I said, those are the coordination nodes. And after the masters come up, we get all the T servers join the cluster, which are the ones which actually hold the data. And also, if you see the PVCs that gets created, each of them have their own PVCs that are bound. Currently, I'm using the storage class that is provided by GCP, which is gonna create SSDs for me, and it bounded to my pods. So this very quickly that Kubernetes kind of simplifies the way that we kind of provision volumes and bootstrap our databases itself. So while this cluster is coming up, I think it's almost done, I guess. And there's like few things that we can do. We can run workloads. Before I do that, I just wanted to show you like what happens behind the scene, like how we orchestrate our stateful sets. uh, so Yugabyte, whenever we create the whenever we do a create universe, right? What happens is behind the scene, the Yugabyte operator fires a Helm deploy of the Yugabyte cluster, and also we have built in all the day two operations that are needed for Yugabyte using the Kubernetes API. So similar to how an operator would do, we have built all those things in the Yugabyte platform. So the first thing would be the master stateful sets and the T-server stateful sets. Those are the ones that will come up, and also they will have the corresponding PV and PVCs provisioned for them from Kubernetes. And since it's a stateful set, we'll have two headless services like YB master headless service and YB T-server headless service, and all the apps which are within the Yugabyte. Let's say if they are in inside Kubernetes cluster, they can just use one of these headless services for connecting to Yugabyte cluster. If the app is outside of a Kubernetes cluster, or if you have like a IDE or something that you want to use against Yugabyte outside of Kubernetes cluster, then we also expose a load balancer for our T servers, so that we have outside access, which can be easily turned off using a flag. We have a flag whether to enable load balancer or not. If we do that, it's like, and that's the power of Kubernetes, right? It simplifies even creating a load balancer, even the networking aspects for us. Cool. And to ensure the high performance, there's like Nipendra touched upon a lot of good things when he was explaining the storage orchestration in Kubernetes. So right now there's like two ways that we are saying that we want to support we will support storage orchestration. One is through local storage, and the remote storage, which is through NFS type. So there are like, each of them has its own advantages and disadvantages, right? With the local storage, obviously the performance will be much higher since the volumes are not network attached. It is right there in the VM. And however, one thing about local storage is like you have to make sure that the pods that get provisioned are provisioned on the same node. So whenever there is a node outage, you'll probably have that pod outage also. Like you'll have a less number of redundancy in your cluster. However, for the remote storage, which kind of supports a pod coming up in a different node and resurrecting the pod and reattaching the volume, you don't have the situation. So obviously, remote storage also nowadays provides high throughput. Like if you're going to AWS, there are like higher IOPS disks that you can attach, SSDs that you can attach through EBS. However, they're kind of expensive, and it's not cost efficient as you scale for like when you scale hundreds of terabytes of data. So it's kind of balance between what you want, high performance versus cost. If cost is not an issue, then we can just use a high ops EBS or a network attached storage on a cloud provider. Cool. The other thing that I wanted to touch upon, one of the other things that we had to keep in mind when we are designing our Kubernetes offering is the pod anti-affinity. We do not want to have similar pods to be scheduled on the same node, right? Like even in a situation where I have three nodes, and if all my T server pods get scheduled in one of the nodes, if that node goes down, so everything, my database is down, right? We don't want the situation to happen. That's why we have pod anti-affinity built in. And also when we move towards Kubernetes clusters which are deployed on multi zones or multi regions, our pod anti-affinity rules will adhere to that, so that the T servers are kind of T servers are the T server pods are deployed in a way that they are distributed on all the available zones and regions. So this is another consideration that we had to do when we were designing our offering for Kubernetes. So the few other things that Kubernetes makes it easier is some of the day two operations. So handling failures, right? The pod failures itself, like pod failures, whenever there is a pod that goes down, Kubernetes automatically resurrects the pod. And Yugabyte behind the scene, what it does is any new pod that is coming into the cluster can join the cluster, and it goes through it goes through the elections, and the node will be let into the cluster. So it kind of seamlessly failures. And we support rolling upgrades, like say when there is new release that comes in, without any downtime you can start doing a rolling upgrade. And also we do support zero downtime scaling, like linear scaling. You can keep adding nodes to the cluster, it seamlessly scale the workload as well, and you can see linear scalings. And there's a really good if you search for YugaByteDB benchmarks, we recently published a YugaByteDB benchmarks where we kind of showcase how we benchmarked our product and how the scaling actually works for relational as well as non-relational workloads. That's a really good read if you are interested in the performance of the database itself. And the third thing is we do support backup and restore with our platform, with Yugabyte platform itself. If you see, we we can do a scheduled backup, or if you go to one of the uh, real ones that we have, we can see a bunch of things, a bunch of backups that we have already created. Where with Yugabyte, what you can do is you can write your backups to S3 or any of your any other NFS mounts you have. Like we support Amazon S3, we support Google Storage, and we also support Azure Storage. You can write your backups to either of those, and also you can restore the backed up cluster to an existing cluster or any new cluster. So the cluster size also need not remain the same. You can have a larger cluster or a smaller cluster depending upon the data set. So all these things we were able to easily allow operators to do using our platform. And Kubernetes constructs were super useful. Or as Kubernetes constructs matured, that's how we are able to get all these seamless day two operations with Yugabyte. So, and extending stateful sets, we want to also support operators. That's something that we are currently working on. So we want to support auto scaling using different parameters, whether it is like say CPU based or a number of requests that are coming in. So based on those metrics, right, we want to be able to scale the cluster out or shrink the cluster depending upon the traffic. So that is something that we are currently working on in order to support auto scaling feature that some of these cloud providers like AWS do. We can quickly, if you are interested in getting started with Yugabyte, you can just go to this link. We have bunch of material out there for you to getting started on your local database as well as on any IaaS of your choice, whether it's Kubernetes or cloud providers or data center. You can quickly go here and get started with YB. Okay. Before I go to the real world example, I just wanted to check if there's any other questions.
They've been answered by Amay, so I think we are good. You
Oh, okay,
continue.
perfect. Okay. So in order to put all these together, right, like obviously we talked about cloud native and cloud native apps and the cloud native databases, right? All those things won't matter much if we cannot have everything work seamlessly together, and if it is easier for application developers to quickly get started with the concepts we talked about, right? So today we are going to show like a classic enterprise app scenario. Earlier in the deck we talked about a bunch of e-commerce applications, right? So we kind of took some of the main requirements of for an e-commerce website, and we created like a mock e-commerce or a demo e-commerce site from our side. So which kind of follows uh, a bunch of these current cloud native stack, we kind of call it. So it's gonna based on React JS, and it's gonna have a Kubernetes cluster which is Istio enabled, so that we can maintain the microservices traffic pattern. And also we are gonna show how we architected all these microservices against YugaByteDB, how the different access patterns we had to think through, whether to use YCQL or YSQL. So we're gonna see the architecture of that. I was just gonna quickly do a demo of our app itself. So this is just like any other e-commerce application you might have seen, right? So we call it as Kronos Marketplace, and we have like bunch of categories here. We have books, we have music, beauty, and electronics, or whatever. And if you go to any of the books, and you can see the description of that, this is like similar to how Amazon would look probably few years I mean probably a decade ago, kind of a thing. We have like around million records in our products data set, so that we could do some good work with that, good data science work also with that. So for now we just use that data set to make this e-commerce application. So along with seeing what each product definition is, we can do add to cart, and we can do like whether check out the cart, right? So this entire thing, if you see, everything is pretty seamless. However, behind the scene, each of these steps that I did, like querying for the products and adding it to the cart, as well as checking out from the cart, all those things are actually served by a different microservice, and all of them are actually currently deployed on Kubernetes. So let me quickly walk you through the architecture itself. So what we are doing is, it's like a very event-based architecture. It's like that's what most of the industry is doing, right? And the way that we have enriched our data set, we kind of did Spring Cloud streams and used Kafka for cleaning our data set and loading it to YugaByteDB using based on the format we wanted, whether it's a SQL or NoSQL. And that's what we used behind the scene for enabling this app. So there's like, this is the high level architecture for our microservice itself. So if you see here, probably this is common for most of the folks these days, how they deploy microservices in a cloud native setup. So we have API gateway, which is responsible for funneling all the requests into other microservices, and each of those microservice goes ahead and access the data in the YugaByteDB cluster. So currently we have three microservices. As I showed you, right? We have a product microservice, which is responsible for showing the product details and the category information and things like that. Since the product, we wanted to have a NoSQL based access for products, because we wanted to have fast point lookups, and also we wanted to have it scale linearly. As and when there is like more number of products that come in, we wanted to be able to scale the table linearly. That's why we went ahead and used YSQL for that. And so that if there is a case where we are kind of serving hundreds of thousands of transactions, or hundreds of thousands of reads and writes, we want to have our product microservice able to manage that. That's why we went with NoSQL, because point lookups will be super fast. So for checkout and cart microservice, if you saw checkout needs a transactional way of making the transactions, right? And also there may be situations where you have a bunch of relationships between the tables that needs to get updated when you do a checkout. Let's just say that when I do a checkout, I want to also make an entry for shipping. So all those things have to happen in a transactional fashion. So we felt we need to have a relational based access for checkout. And also cart microservice. Cart, we could do either YCQL or YSQL. Uh, but based on the research what we did, most of the e-commerce applications, they use relational or RDBMS system for backing their carts. That's why we went ahead and used cart microservice for YSQL. So if you see here, with a single database, I can serve multiple different access patterns. That's kind of like the advantages of using a cloud native database like YugaByteDB. So one other thing, all these things are actually running inside a Kubernetes cluster, which is enabled with Istio, so that Istio kind of provides a bunch of things like service discovery, and it provides capabilities for doing traffic testing, A/B testing, like blue-green testing. So all those things are like some of the things which app developer or a cloud native architect will think about these days when deploying their cloud native applications onto the cloud. So any questions on the app itself or the app architecture? Okay. Can Yugabyte be a good concurrent for data streaming use case for ML model training? Uh, so whenever we are doing ML training, we don't have the streaming capability that we provide is through we call it as a CDC. So Yugabyte can be a good way for you to store like say intermediate results or like your end results itself, or Yugabyte can be a good place where you load your data set. So for streaming, we kind of provide a Kafka connector, which we can use to sync the data into Yugabyte or read the data from Yugabyte. That's how we see where Yugabyte fits in the data streaming use case. Cool. Actually, that's all I had as part of this presentation. Hopefully, you guys learned a bit about distributed SQL and how we orchestrate on Kubernetes. And we welcome community contributions. We are a Apache 2.0 project, and we rely on community traction. And it would be great if you guys can go ahead and give a star for us in our Git repo. And also, we are hiring. Like if you are looking to solve complex distributed SQL problems, like algorithm problems, you can go to our website and see we have positions open. I think even in India we have positions open, and if you are elsewhere in the world, in North America, we have positions open in North America as well. Again, to stress, you can write us if you want Yugabyte swag. You can write to us. You'll get some swag from Yugabyte if you star us.
So do you have an office in India? Yugabyte has an office in India?
We do not. We are a distributed company, so it doesn't matter, I guess.
Okay.
I mean, we have people all over. Ame is currently in India. Is working from India.
Okay. Thanks, Amir, for answering all the questions what we had on YouTube and here. And thanks everyone for joining in for this session. Hope you liked it. And of course, we'll be doing the next sessions in future. And if you want to kind of present, most welcome. So I had an idea of hybrid cloud. Why Kubernetes for hybrid cloud? That's one thing I had. And then other idea was for the API gateways. Like what are the API gateways you have in Kubernetes? So if anybody were to kind of come and talk about them, most welcome to please reach out to me and we can have a session. And thanks, Nikhil, for this excellent session. I think everybody liked it, and that's what we are getting those comments on the chat.
Yeah.
Thanks everyone, and hope to see you soon in the next sessions.
Thanks for hosting us, Nipendra. It was great talking
No
to you.
worries. No worries, man. Thank you. Thank you, everyone. See you soon. Bye bye.
Thanks, you. Have a good one.